In this video, we're going to be performing truss analysis using the method of joints. For this example, we're going to be calculating the forces in the Warren truss below. Before we begin, we need to calculate the angles in the truss. Taking one of the triangles, we can note that the width is 6.9 divided by 4 and the height is 1.5. However, we can split this into a right angle triangle if we bisect it vertically. To drawing a vertical line, we can split this into two right angle triangles, where the width is going to be 0.86 meters and the perpendicular height is 1.5 meters. So using trigonometry, we can work out that the angle is equal to inverse tan of the opposite over the adjacent. This is inverse tan of 1.5 divided by 0.86. This gives us an angle of 60 degrees. Noting the symmetry in the triangles, so if the angle in this triangle is 60 on the left, then it's also 60 on the right, which means the top angle is also 60 degrees. So in this particular Warren truss, all of the triangles are equilateral triangles with 60-degree angles. The first step is to calculate the support reactions. So looking at the two supports, we need to work out what type of support reactions we're going to have at each of those supports. So at support A, this is a pin joint. It allows rotation, but it prevents movement in both the X and the Y directions. Therefore, we're going to have two support reactions. We're going to have AY and AX. At support G, this is a roller, so therefore it allows movement in the horizontal direction. It allows rotation, and it's only going to provide us a support reaction in the y direction, gy. So to find AX, we're going to consider the sum of the forces in the x direction. So taking any forces to the right as positive and any to the left as negative, we want to add up all of the forces in the x direction and make these equal to 0. So the only force we have in the x direction is AX. Therefore, we get that AX is equal to 0. So I can remove AX from our diagram. Now we want to take moments at A. So taking anything which is a counterclockwise moment as being positive and any clockwise moments as being negative, we get that the sum of all of moments at A is going to be equal to 0. So moments are force times by distance. So we can ignore AY because this is a distance of 0 from A. So we'd multiply this by 0, which will cancel it out. So the next force we have is the 10 kilonewtons. So if we fix A and press down onto the truss from the top, this would rotate the truss in a clockwise direction, which means that we need to take this as negative moments. Therefore, we get minus 10 times 0.86. The next force we have is the 15 kilonewtons. So again, fixing A and pressing down on top of the truss, this would turn the truss in a clockwise direction, meaning this is also negative. Therefore, we get minus 15 times 4.31. Finally, we have gy. So since we're assuming this is upwards, if we fix A and press up from underneath the truss at G, this would rotate the truss in a counterclockwise direction. This means that this generates positive moments. So to get the moments, we take gy and multiply it by 6.9, which is the distance of gy from A. And all of these three added together equal to 0. So rearranging this equation, so bringing the minus 10 times 0.86 and the minus 15 times 4.3 over to the right-hand side, they become positive. Dividing by the 6.9, this gives us a value for gy of 10.63 kilonewtons. I can add this onto the diagram. Then finally, to calculate the support at A, I'm going to take the sum of the forces in the y direction is equal to 0. So choosing the direction up as positive and the downward direction as negative, this gives me AY, which is up, is positive, plus the 10.63 support reaction at G is positive, minus the 10 and minus the 15 is equal to 0. So solving this, we get that AY is 14.37 kilonewtons. And I can add this onto the diagram as well. So the next step is to perform the method of joints. So we could start at either end. So I'm going to start over at the left at joint A. So to do this, I'm going to draw a free body diagram of the joint A and the forces acting on this. So we assume in this truss that all of the joints are acting under tension. So we have the AY, the support reaction, acting upwards. We have a force through the member AB, which I will call FAB. And we have a force through the member AJ, which I'll call FAJ. Remembering that FAB is acting at 60 degrees to the horizontal. So what I need to do now is to resolve the force FAB into a vertical and a horizontal component. So we know that FAB is acting at 60 degrees to the horizontal. So from trigonometry, the opposite is the vertical component. So the opposite and the hypotenuse mean that we're using sine. So the vertical component will be FAB sine 60. And the horizontal component is the adjacent. So this will be FAB cos 60. Remembering that symmetry that we have in the truss, this means for this particular example, all of our vertical components are going to be sine 60 times the hypotenuse, and all of our adjacent components are going to be cos 60 times by the hypotenuse. So now we can take the sum of the forces in the y direction, remembering that these add up to 0. So again, anything going upwards is positive and downwards is negative. Acting in the y direction at joint A, we have 14.37, which is positive as it goes up. And we also have FAB sine 60, the vertical component of FAB, which is also positive. So the sum of these two is 0. Let's bring the 14.37 over to the other side where it becomes negative, and dividing by the sine 60, we get that FAB is minus 16.59 kilonewtons. So this just means that this is acting in the opposite direction to what we assumed. It's under compression rather than tension. It's now taking the sum in the horizontal direction. So taking anything to the right as positive and anything to the left as negative. At the joint A, we have FAJ, and we also have that horizontal component of FAB, which is FAB cos 60. Therefore, FAJ plus FAB cos 60 equals 0. So rearranging by bringing the FAB cos 60 over to the other side, and using the FAB is 16.59, we get that FAJ is 8.3 kilonewtons, and since the sign is positive, it means that this is under tension. So I'm going to add these onto my diagram. Now we can repeat this process, moving on to the next joint. So moving on to joint B, I draw my free body diagram. So now taking the sum of the forces in the y direction and adding these up to 0. So in the y direction, positively, I have FAB sine 60. So this is 16.59 sine 60. Then acting downwards, I have the 10 kilonewtons. And I also have the vertical component of FBJ, which I said is FBJ sine 60. So all of these added together equal to 0. So I can rearrange and solve this equation, and this gives me that FBJ is 5.04 kilonewtons. Since it's positive, it means that this member is under tension. And then adding up all of the forces in the x direction, equating these to 0. So in the positive direction, to the right, I have FAB. So taking the horizontal component, I get 16.59 cos 60, plus FBC is also going to the right, plus I have that horizontal component of FBJ, which is 5.04 cos 60. And all of these add up to 0. So rearranging and solving, I get that FBC is minus 10.82 kilonewtons. Again, the minus sign just means that this member is under compression rather than tension. So I can add these onto my diagram. And then I move along to the next joint. So moving on to joint J, I repeat the same process. So drawing a free body diagram, then taking the sum in the y direction. This gives me 5.04 sine 60 plus FJC sine 60 is equal to 0. So both of these are positive because they both act in the upward direction. Rearranging and solving, I get that FJC is minus 5.04 kilonewtons. So again, this member is under compression rather than tension. Then taking the sum in the horizontal direction and adding these up to 0. So this gives me minus 8.3 as it acts to the left, minus 5.04 cos 60 as this acts to the left, then adding the components to the right, the FJI, and also adding the FJC, which I know is minus 5.04, multiplied by the cos 60, and equating these to 0. So rearranging and solving, I get that FJI is 13.34 kilonewtons. Since it's positive, it means our assumption was correct and it's acting under tension. And we can move along to the next joint, which is joint C. Again, drawing a free body diagram, taking the sum of the forces in the y direction, so anything acting upwards is positive and down is negative. So acting up, I have the vertical component of the FJC, 5.04 sine 60, and then I'm subtracting the downward force, which is the vertical component of FIC, which is FCI sine 60. And equating these to 0, I can rearrange to solve. The FCI is 5.04 kilonewtons, so it's acting under tension. And taking the sum in the x direction, so the forces acting to the right is the 10.82. Also, I have the 5.04 cos 60 from the FJC, plus the FCD, plus I have the horizontal component of FCI, which is 5.04 cos 60, and all of these add up to 0. Rearranging and solving, I get that FCD is minus 15.86 kilonewtons, so it's acting under compression. Moving on to the next joint, joint I, drawing the free body diagram, and then taking the sum of the forces in the y direction. So the forces going up is the 5.04 sine 60 to take that vertical component of the FCI, plus the vertical component of FID, which is FID sine 60, and these equal to 0. Rearranging and solving, FID is minus 5.04 kilonewtons, so it's under compression. And taking the sum in the x direction, I have minus 13.34 as FJI goes to the left, minus 5.04 cos 60 as the FCI acts to the left, plus the FIH, and I also have plus FID cos 60, which is minus 5.04 cos 60, and these add up to 0. Rearranging and solving, FIH is 18.38 kilonewtons, so it's under tension. Moving on to the next joint, joint D, I draw the free body diagram, again taking the sum of the forces in the y direction. So the positive forces in the y direction is the 5.04. So to make this the vertical component, I multiply it by the sine 60. Then acting downwards, I have the 15 kilonewtons above. And I also have to subtract the FDH sine 60. And these add up to 0. Rearranging and solving, I get that FDH is minus 12.28 kilonewtons, so it's under compression. And taking the sum in the x direction, So in the positive direction to the right, I have 15.86. I have 5.04 cos 60. I have the plus FDE. And then I also have the plus FDH cos 60, which is minus 12.28 cos 60. And these add up to 0. Rearranging and solving, I get the FDE is minus 12.24 kilonewtons, so it's under compression. Moving along to joint H, I draw the free body diagram, take the sum in the y direction. So acting downwards, I have minus 12.28 sine 60, and upwards, I have the FHE sine 60, and these add up to 0. So solving, I get that FHE is 12.28 kilonewtons, so it's under tension. Taking the sum in the x direction, acting to the left, I have minus 18.38. Then acting to the right, I have plus 12.28 cos 60. I also have plus FHG, and I have plus FHE cos 60, which is 12.28 cos 60, and these add up to 0. Rearranging and solving, I get FHG is 6.1 kilonewtons, so it's acting under tension. Then moving on to joint E to find the last force. So I draw my free body diagram, take the sum of the forces in the y direction. So I have the minus 12.28 sine 60 for FHE. I have minus FEG sine 60, and these add up to 0. So rearranging and solving, I get FEG is minus 12.28. And then I can do a quick check as well. So taking the sum of the forces in the x direction, I get 12.24. I have the minus 12.28 cos 60 for FHE, and I have minus FEG cos 60, which is equal to 0. So rearranging and solving, I get that FEG is minus 12.28, which verifies my answer from before. For a quick final check, I can do the method of joints at G just to check that the forces add up to 0 and I've not made a mistake. So drawing my free body diagram, I can check that the forces in the y direction add up to 0, and I can also check that the forces in the x direction add up to 0. So therefore we've found the forces in all of the members in the Warren Truss.